So we ended up yesterday doing this. We talked about jet acceleration. I told you that there are two regions for the acceleration. Region 1 is an efficient acceleration. Second region is the non-efficient acceleration, where to get an efficient acceleration, you need, in the rest frame, you need roughly equilibrium between toroidal and poloidal field. And in the second acceleration regime, you are dominated by toroidal field rather than poloidal field in the rest frame. What I want to do today is I want to try to give you some feeling about what it means. What does magnetic acceleration means? And then we're going to discuss about when this acceleration is efficient, when it is not efficient. So to understand why is this acceleration efficient, let's first talk about how magnetic field change. Okay? So if we, to remind you, we are in a situation where we have a steady state. Nothing changes in the system. We have a steady flow. Okay? And then in a steady state situation, we have a flux conservation of magnetic field. So flux conservation tells us that in the lab frame, BP is proportional to 1 over r square, while B phi is proportional to 1 over r. Okay? Now let's suppose that we are in a situation where the matter accelerates efficiently. So we are in the first acceleration regime. Gamma is equal to gamma 1. Okay? And when the cylindrical radius is much larger than the light cylinder radius, okay, when r is much larger than RL, then gamma just changes linearly with r. Okay? So in this situation, gamma is just proportional to r. Okay? We accelerate linearly with the cylindrical radius. Okay? So let's write these quantities in the rest frame. So again, we are accelerating along poloidal direction. So BP doesn't change. Okay? So in the rest frame, BP is just equal to BP. However, B phi is proportional to, not proportional, is equal to B phi in the lab frame divided by gamma, which is proportional to 1 over r square. Okay? This is also 1 over r square. Okay? So both quantities change together like 1 over r square. But remember that I told you that B phi, flux conservation, tells us that B phi should change like 1 over r. So in the rest frame, B phi changes faster than what it wants to be. So where does this extra magnetic energy went? Remember, we have energy conservation. This energy, B phi changes faster. Remember, magnetic pressure, which is the energy density, is the B phi square. So B phi square, the magnetic pressure drops faster than what it wants to do. So I have an excess energy. Where does this excess energy go to? Acceleration, exactly. The excess energy is going to accelerating the jet, increasing the rest mass energy density, and this is the jet acceleration. Okay? So B phi is the component that brings us the jet acceleration. So let's try to picture that. Okay? I find it very useful when you have sort of a picture in your head that what is going on. So in order to understand that, let's imagine a spring. Okay, magnetic field look kind of like a spring. Okay? When large B phi means that the spring is compressed, the density of the coil is very high, and when B phi is low, the spring is decompressed. Okay? So this is large B phi. Okay? And this is small B phi. Okay? So when you're compressing the spring, what is happening? the spring has tension. So what does it do? It applies force that objects your compression and try to make the spring expand. So the spring wants B phi to be smaller. Okay? So let's imagine that this spring, that the flow is actually the spring as it goes. So as it goes along in the rest frame, the spring wants to compress. Why? Because B phi drops slower than BP. So B phi drops slower than BP means that B phi, as the flow continues to expand, B phi is increasing relative to BP. So the spring, as the spring moves, it tries to compress, but it has tension. The tension tells it, do not compress. So it's expanding the spring. It's making sure, this tension is making sure that B phi does not increase. So this gentle push that the spring is doing to the flow, this gentle push is the acceleration. Okay? So the spring keeps on pushing and preventing itself from compressing, and this is the acceleration. Okay? So we understand what acceleration means, but in order to get an acceleration, I need a tension to work. Okay? I need the spring constant to be constant, this K thing. Okay? And tension is a global quantity. What does it mean? It means that each point along the spring needs to be aware that it's part of a spring. The 2 points in the other side of the spring need to communicate with each other. So this point we said, oh, that point starts to move, so it means that I have tension, so I need to react to that. Okay? So this means that I need to have a causal contact around the jet. Information needs to be able to move around the jet to connect all the points. Okay? Efficient acceleration, regime 1, okay? So let's try to understand what does a strong causal contact mean. So what I want to do now is define you the meaning of strong causal contact. Okay? So imagine that we have a fluid element that is moving along some radial trajectory. Okay? At time t equals 0, it is located at a distance r from the center. Okay? And now the particle is double its radius. It moves from r to 2r. Okay? So I'm moving from r to 2r. Okay? The flow is moving with a velocity v. Okay? And the time it takes it to cover this distance is just t is equal to r divided v is equal to beta c, and r divided by beta c. Okay? Now, this particle is sending a beam of light to the axis. And what I want to do is I want this beam of light to be able to reach the particle by the time it's double its radius. This means that the particle can communicate with the axis. Information can flow from the axis to the particle during the time that the particle is moving. This is a strong causal contact. Okay? So by the time r doubles its radius, light can reach it from the axis. Okay? Now let's look at the situation from a system that moves upward with the particle. In this system, the particle is moving sideways. Okay? Because we are moving with the particle. So within a system O tag moves with the particle. In the z direction. Okay? So in this system, the particle moves sideways in a velocity. Okay? So the distance that the particle is covering, this distance, okay, this is, let's call it x tag. So x tag is equal to r times sinus theta. Okay? This is just the x component of this path. Okay? And the time that the particle is moving, we're measuring time, remember, in the rest frame, because we're measuring time within the O-tau system. This time is just t divided by gamma. Okay? So the velocity that the particle is moving in the rest frame is just x tag divided by t tag, which is, so this is r divided by gamma beta c. Okay? So I just take x tag divided by t tag, and what I get is gamma beta sinus theta c. Okay? Now I want this thing to be smaller than c. So I want u tag to be smaller than c, and what I get is that gamma beta sinus theta is smaller than 1, and in small angles and large Lorentz factor, this is roughly gamma theta smaller than 1. So this is the definition of strong causal contact. In strong causal contact, there is a connection between the angle that I'm expanding and my Lorentz factor. If I continue to increasing on radial direction, at some point, gamma theta will be larger than 1, and I will lose strong causal contact. Remember that when we discussed relativistic beaming, I told you that all the radiation is beamed into an opening angle which is equal to 1 over the Lorentz factor? Theta is equal to 1 over the Lorentz factor is exactly the limit between strong causal contact and weak causal contact. Okay? So relativistic beaming is connected also with this quantity of strong causal contact. Okay? Let's talk about it. Good question, because we're going to talk about it now. So our particle is now, a fluid element within our jet expands radially, and at some point, the strong causal contact is broken. So when the strong causal contact is broken, this point can no longer efficiently communicate with that point. So it means that the tension in the spring is not working well. Because this point takes time until it realizes, okay, this point contracted, so now I react, but I'm reacting in delay. So it means that the spring becoming softer. So if the spring becoming softer as I continue to expand, remember when I'm expanding, I want to compress the spring, I'm able to compress the spring more. So my acceleration becomes inefficient. Okay? But then what is happening when my acceleration becomes inefficient? Okay, we're now in a regime where we are in a weak causal contact. So when my acceleration becomes inefficient, b phi drops slower than 1 over r squared. Okay? b phi in the rest frame, okay, gamma now goes like, let's say, r to the power of 1 minus delta. It goes slower than just linear with r. Okay? Thus, b phi, which is equal to b phi divided by gamma, is proportional to 1 over r square minus delta. Okay? And this is larger than 1 over r square, which is proportional to bp. So b phi is now larger than bp. What's happened then when b phi is larger than bp? Look over there. Gamma 2, second acceleration regime. So now I'm accelerating not according to how the spring is compressed. The second acceleration regime, remember, is we are accelerating according to the curvature radius of the poloidal field. Okay? That's what I showed you, that we have some jet with some curvature in the poloidal direction. I will accelerate according to the curvature radius here. It's like the spring now is a little bit tilted, and this tilt gives the tension in this direction, the poloidal direction. So I do not need this connection around the spring anymore. All I need to do is that this spring is now tilted and it's kind of pushing sideways, and this gentle push sideways, this is what gives me the second acceleration regime. Okay? So now the spring is very soft, but what I'm doing is I'm bending it like that. As I'm bending it like that, it sort of rejects the bending. It tries to move backwards, and these motions, these are the second acceleration regime. But to do that, there is another limit that I need to maintain. How fast can the spring move sideways? How fast can information travel in hydrodynamic gas? So not Alfvén speed, because Alfvén speed is along the spring, and we are moving sideways. It's almost the Alfvén speed. It's the fast magnetosonic speed. Okay, you remember when Matt told you there are three types of sound velocity in magnetic field. There is an Alfvén velocity, which is along the magnetic fields, and there are the magnetosonic, fast or slow magnetosonic velocities, which are sideways, moving sideways. But when the plasma is cold, the fast magnetosonics is very, very similar to the Alfvén velocity. Okay? So the limit that we have now in order for the spring to react is that we need to be fast, we need to be slower than the fast magnetosonic velocity. Okay? In other words, this sideways motion, okay, which is actually, I didn't write u here for nothing, because this is actually the definition of u, the forward velocity. Okay? So the forward velocity u, which is equal to gamma beta sinus theta, okay, c, but let's drop c because I'm going to drop it on the other side, needs to be smaller than u fast. Okay? If I'm moving faster than the fast magnetosonic velocity, then the fact that the spring is trying to push back doesn't matter, because I'm faster than the rate that the spring can propagate. So if I'm moving faster than that, I can no longer accelerate. Okay? So let's derive the condition from that. So the fast magnetosonic velocity is roughly equal at high sigma values to square root of a parameter which is known as sigma. Let me define you what sigma means. Okay? So sigma is just the ratio of b squared divided by 4 pi rho c squared. Okay? This is very similar to another quantity that you may or may have not learned about, which is known as the specific enthalpy, and which is marked as H. And the specific enthalpy, right, is just 4p, which is the enthalpy of a gas, of a hydrodynamic gas, divided by rho c squared. Okay? So in hydrodynamic, there is this quantity, which is unitless, and it tells you how, this is basically the enthalpy per unit mass. Sigma, b squared divided by 4 pi, is the enthalpy of the magnetic field. So this is the magnetic enthalpy per unit mass. The importance of this quantity tells you how much energy eventually I can disperse to each mass unit if I want to accelerate the flow. So this tells me that the initial value of sigma tells me how much energy I have in my bank, and this energy I can theoretically eventually put in the flow into bulk motion. Okay, this is my bank. So just like in hydrodynamic, when there is a conservation, like when we discussed, in the first lesson we derived the Bernoulli conservation, the relativistic Bernoulli conservation equation, which was told us that gamma W divided by rho is constant. Okay, this is how we got the acceleration of hydrodynamic jet. This means that H gamma is constant, because W divided by rho is just this constant quantity. So the Bernoulli equation just tells us that H gamma is constant. In magnetic field, when we have when we also add magnetic field, okay, the combination of sigma plus h, this is the total enthalpy per unit mass that I have. So in the magnetic case, the quantity that is conserved is actually sigma plus h. And since we're talking in cold flow, all my energy is in magnetic field, okay? H, P, H is about, sorry, this is, yes, so this is like, something is, yes, this is not H, my mistake, because W, yes, H is this, my mistake, 1 plus 4p divided by rho c square, okay, which is W divided by rho, and W is equal to rho c square plus 4p divided by rho, okay, so this is H, okay, so we still have H gamma is equal constant. I forgot the rest mass energy density here, okay, so when we are talking, when the flow is cold and we don't have any thermal pressure, this part is 0 and H is 1. Okay? So this goes to sigma plus 1 is conserved, is equal to constant, to some constant. Okay? And I call this constant sigma 0. It basically should be sigma 0 plus 1, but if sigma 0 is high, I just call this constant sigma 0. So the relation that I have is that gamma beta sinus theta is smaller than square root of sigma. And I also have the conservation that sigma plus 1, I forgot gamma here, right? Because just like I have gamma h here, I need to have gamma sigma plus h here. So this goes like to gamma sigma plus 1 is constant. So I have the connection of gamma times sigma plus 1 is equal to sigma 0 plus 1, which is roughly sigma 0. Okay? So now I can extract gamma from these two equations. So this means that sigma is equal to sigma 0 divided by gamma minus 1, which is roughly sigma 0 divided by gamma. And now I take this quantity and I put it here, okay? And what I get is that I get that gamma theta, I'm already moving to high Lorentz factor, small angle, I already did this, this approximation, is smaller than square root of sigma 0 divided by gamma, and this means that gamma is smaller than sigma 0 divided by theta square to the power of 1/3. So the condition that I need to be slower than the fast magnetosonic velocity gives me this. Now in large theta, when theta is large, sinus theta is roughly 1. So when theta is large, okay, I'm getting that gamma is smaller than sigma 0 to the power of 1/3. When theta is larger than 1, okay, than 1 radian. Okay? Do you recognize this, this inequality? Okay. In magnetic field, there is something that is known as the sigma problem. This is the sigma problem. What does it mean? It means that if I have something that is accelerating on radial trajectories, what will happen to it? It will first accelerate linearly, okay? At some point, it will lose strong causal contact. It will start to accelerate very inefficiently until it will reach this. Gamma is smaller than sigma to the power of 1/3. And at that point, it will stop accelerating. But if I started with very large sigma, if I started with sigma of 1,000, let's say, okay? So sigma of 1,000, okay? Sigma is the specific energy density, right? Sigma tells me that if I started with this, since this quantity is preserved, okay? Where is it? Here. Since this quantity is preserved, okay? And I'm starting with sigma equal 1,000. It means that if I'm accelerating efficiently indefinitely, what is the largest Lorentz factor that I can get? This is my bank, and this is the equations that need to be kept. This is the conservation equation. If I'm starting on the right-hand side, I have 1,000. This sigma, as I'm accelerating, magnetic field is decreasing. So sigma is also decreasing, right? So I'm starting at a large sigma, I'm accelerating. I can decrease sigma to what value? Basically? 0. And when sigma is 0, what will be gamma? 1,000. So the initial specific enthalpy tells me what the final Lorentz factor will be. So if I have an initial specific energy density of 1,000, it means that theoretically I should accelerate up to a Lorentz factor of 1,000. But when I look strong causal contact here, I cannot accelerate anymore. So what is my final Lorentz factor? 10. It means that still 10 times of my energy is in magnetic field than what I have. Okay? So it means that I could not utilize all my magnetic field to bulk motion. I am too slow. And this is the sigma problem. Okay? How can I solve the sigma problem? What comes to my aid? If theta is very small, okay, then it means that I can reach larger and larger Lorentz factor. So magnetic jets, the narrower they are, the more efficient they can accelerate. Why does this happen? Because small opening angle allow me to remain in strong causal contact for a longer time. Okay? So now let's try to see whether I can maintain strong causal contact. What is the condition to maintain strong causal contact all the way till the end of my acceleration? Can I do that? Okay? So let's see what is the most efficient way that magnetic jets can accelerate. So I will erase, you're probably copying this, so I will erase that. Okay? Efficient acceleration. So to have an efficient acceleration, the condition was, I erased it. So the condition was, let's write it here, strong contact. So gamma theta is smaller than 1. Weak contact, gamma is smaller than sigma 0 divided by theta square, the power of 1/3. Okay? So to get strong causal contact all the way, I need always to maintain this. That gamma theta smaller or equal to 1. Okay? So let's draw a curve here. Okay? And in this case, I'm accelerating efficiently. So if I'm accelerating efficiently, gamma is equal to R divided by RL. Okay? Efficient acceleration, first regime. Okay? Now what is theta? What is the definition of theta? Remember, I'm accelerating on a curved line. So what is theta on each location here? Can you define theta? Theta is the angle that I'm changing. Okay, let's plot a small triangle here. Okay, this is dr. This is dz, and this is theta, right? When I'm completely perpendicular, theta is 0. So what is theta? Theta is tangent, so it's just dr to dz. So theta is equal to dr dz. So my condition is, the limit condition is that r divided by rl times dr dz is equal to 1. This is a regular, an ordinary differential equation. We can move z to the other side, and we can solve it. And what we get is that r square, let me write it here, we get that r square divided by 2r is RL is equal to z, okay? Or z is proportional to r square. What is that? This is a parabola, okay? So the condition to accelerate efficiently all the way to maintain strong causal contact on the edge of this curve is that I'm accelerating like a parabola. Yesterday I told you that the curvature radius is defined by the derivative of the r by the second derivative of the r dz to the power of -1. Okay? So if we take some general curve, z is proportional to r to the power of alpha, I'm getting that the curvature radius is r to the power of alpha -1. Okay? This is not the curvature radius. Sorry. This is, I think, yes. Yes, because wait. Just want to make sure that I'm not misleading you. One moment. No, this is gamma. Our curve is just r to the power of, yes. This is gamma. Yes, this is gamma. Okay? So when you do that, you take a general shape of the curve. The second regime gamma scales like r to the power of alpha -1. Okay? Okay. So now we understand that. We understand how efficient acceleration can be reached. So let's wrap up all that we learned and try to follow a particle and it moves along a curve where we change the slope of the curve. And we see, and let's see what is happening to the Lorentz factor of the particle. So this will be the concluding part of the acceleration section. So let's conclude. So here is my origin. And let's draw first a parabola shape, a line that goes like a parabola. This is alpha equal 2. Okay, this is a parabola. And as we said before, when I'm accelerating in a parabola when alpha is equal to, my acceleration is linear with the radius all the way up. So here what I have is that gamma is proportional to gamma 1, which is proportional to r. So any jets that are collimated into angles that are smaller than this, all this regime, I have efficient acceleration. Okay? Now, this is a radial curve. Okay? This is alpha equal 1. And let's look at the situation where alpha is somewhere between is smaller than 2 and larger than 1. Okay? So what will happen here? I will accelerate up to a point. We'll mark it as a star. Okay? And star means that gamma is equal to dr dz, which is 1 over theta. Okay? So I will accelerate, since I'm opening faster than a parabola, I will reach at some point a location where gamma is equal 1 over theta. Up to that point, I have gamma 1. I'm accelerating like r. Okay, gamma is proportional to r. Above this point, what is happening? What am I losing? Above this point, gamma is larger than 1 over theta. So what did I lose? Strong causal contact. So in what regime am I? The weak causal contact regime. I'm still faster than the fast magnetosonic velocity. So now I moved from the first acceleration regime to the second acceleration regime. I moved here. Okay? So I'm accelerating like r to the power of alpha minus 1. Okay? So now gamma is proportional to r to the alpha minus 1. Okay? And since alpha is smaller than 2, you can see that this thing is slower than that. Okay? I'm continuing to accelerate. I'm still accelerating like a power law, but this power law is slower now. But eventually I will reach a point, this circle, and this circle tells me that gamma now is equal to sigma 0 divided by theta square to the power of 1/3. Okay? At this point, I'm so fast that I'm becoming super fast magnetosonic. And from this point on, what is happening? I stop accelerating. What actually happens is that I'm not exactly stop accelerating, but my gamma is now changing logarithmically with r, which is a very, very, very small rate of acceleration. So above this, gamma is proportional to log r. Okay? So this is curves that are between parabola and linear. Now let's look at radial curves. So in radial curves, I'm accelerating until what point? I'm accelerating efficiently until what point? Again, what will happen eventually? My theta now is constant. My gamma is increasing. At some point, what will happen? Gamma theta will become 1. And I will lose strong causal contact. So at this point, that will happen before that point, here I'm losing strong causal contact. So above this point, I should accelerate like the second acceleration regime. However, the second acceleration regime now alpha is equal 1. Okay, so this is basically 0. So I should basically stop accelerating at that point on a linear curve. However, I will continue to accelerate again something like a logarithmic acceleration. So above this point, r gamma is proportional to r to alpha minus 1, which is proportional to r to the power of 0 times log r. Because the log r is coming from, there is a constant here, c, which this constant is actually changing logarithmically with r. So this is where the log r is coming from. If my curve is now have alpha which is smaller than 1, the jet opens up. And so even when the jet opens up, I still have a regime where I'm still strongly causally connected. So I still have a regime here where gamma will be proportional to r. But beyond this regime, I'm losing strong causal contact and I'm actually starting to slow down. Okay, so here I have slowing down. Gamma is proportional to r to alpha minus 1, and this is smaller than, and this scales, and this is smaller than 1, because alpha is smaller than 1. Okay? So these are the different regimes of acceleration in magnetic jet. More complicated than hydrodynamic jet, but not infinitely complicated.
Is equal to 1 and logarithm 1/3 power.
Sorry?
Logarithm 1/3 power for alpha is equal to 1.
Here.
Here.
Okay. Okay. So it's more efficient than logarithmically, but still up to sigma. Yes, but still very slow.
1/3 power.
This one. So it's even slower than what I said. Okay. Okay? Yes?
Why doesn't this lines cross jump?
Sorry?
What doesn't this line cross jump?
These are different jets. What I'm discussing here are different curves. Okay, each curve stands by itself. It's not the same jet. These are different jets. This is parabolic jet. This is jet that changes a little bit slower than parabolic. This is a jet that goes radially, and this is a jet that opens up. And all this is in a steady state. Okay? This is different than when a jet breaks up from a star, it opens up, but it has a transitory, a state that is transiting. This is not a steady state. In this case, we have like a reverse shock going into the flow. Things changes now. This is a different situation than a breakout of a jet. This is a steady state. This is a jet that does not change with time. Okay, this is important comment. Any questions about that? Yes?
So magnetic fields don't do work. How are the particles actually accelerated?
So, if you pass a sound wave through magnetic field, you basically start to move them like that, right? So you basically have dissipation. And this dissipation is the work. This dissipation is the decrease in the magnetic field. Okay? So that's the work. Another question, yes.
So these particles are moving relativistically. And so in the rest frame, there might be magnetic fields, but if we're moving relativistically, those magnetic fields can have some electric field component.
Yes, there is always, we're working in a situation where the flow is force-free. So it means that you have two components of magnetic field, poloidal, toroidal, and you also have electric field that is perpendicular to these two components. This E, the perpendicular E, this is what gives you the drift velocity. Remember that all of our definition here, gamma, is basically the drift velocity. So in order to have a drift velocity, you must have an electric field, and this electric field is perpendicular to B phi. So the cross product of E cross B, this is what gives you the drift velocity, and this is the gamma. Okay? So we started with a situation when we had the electric field. On the surface, remember, we had an E cross B, and that gives us the Poynting flux and also the drift velocity. This is how we started, so the situation just continues like that. Yes?
Is it possible to make a non-monotonic dependence of R as a function of Z, or we need an external pressure for that?
When you start to play, to get all of this, you need external pressure. The magnetic field in vacuum will try to expand like that, to expand radially. So if you want anything that is not radial, you need some external pressure to push you inwards. And the non-monotonical behavior means that your pressure behaves differently with altitude.
Like, can we make a nozzle?
Yes, we can. We can. If I will have time, I will show you. Okay? Now what I want to move on, and I want to move on to a completely different subject. Okay, we're finished with acceleration. I want to talk a little bit about jet stability. Okay? So, now let's move to jets that are cylindrical, because this is the simplest jets that we know. Okay, we had our jet, it accelerated, and then it turned cylindrical. Okay, so we're discussing here cylindrical jets. So this is our jet. It has some external pressure outside. It has magnetic field inward, poloidal, toroidal, with some structure. And it also has a force balance. Okay? So force balance tells me that the total force in here, okay, the pressure in the jet is equal to the pressure in the external medium. Okay, and the force balance, since things are steady state, means that each particle feels zero forces around him. Okay, so force balance equations and when I will put the notes, I will show you how to derive it, but for now I will just write the equations, is 1 divided by 8 pi times dB squared to dr plus b phi squared divided by 4 pi r is equal to 0. This is the force balance equation in cylindrical jets. In jets that open up is a little bit more complicated. Again, it's in the note. What is each part? This is F. What does each part means? Okay? What is B squared divided by 8 pi? Magnetic pressure. And what is the derivative dB squared divided by dr? It's pressure gradient, it's grad P. Okay, so this is grad P, like in hydrojet. What is this quantity? This quantity represents the tension of the magnetic field. Remember that magnetic field has tension. So what does this tension do? A magnetic field acts like a rubber band. If I take a rubber band and I expand it, it wants to contract again. Okay, the tension, if I have a curve here, this is basically the same thing as the curvature tension. Okay, if I have a curve and I'm expanding it, what it wants to do is it wants to straighten up because I have a tension. So at each point, there is a force that tries to push me back in. This thing presses inward, and this thing presses inward. And the value of this force is just this, b phi divided by 4 r pi r. R is here is the curvature radius. It's again curvature radius thing. So since I have a cylindrical thing, the curvature radius is just the radius. Okay? So this is the force balance equation. Now, let's look at what this force balance equation tells us about the structure of the magnetic field in the jet when we had two regimes. Okay? So, in the first regime, remember, we accelerated efficiently. So suppose that we accelerate efficiently and the jet turns cylindrical. So in this case, in every point in the jet, b phi is smaller or equal to bp. Okay? So and again, what I'm doing here, I just want to stress that everything here is in the rest frame. Well? This is total B. This is b phi square plus bp square. This is total B. Okay? Because I want total pressure. Okay, so in this regime, what I have is that gamma j, remember, is equal to square root of 1 plus r divided by rl square. Okay? And b phi in the lab frame, which is equal to r divided by rl times bp, is equal to r divided by rl times bp. What I wrote here is just the definition of b phi. This is how we define b phi. Omega r divided by c, or r divided by rl. Now bp, since bp does not goes any Lorentz transformation because everything moves along bp, so this is equal to bp in the rest frame. Okay? So this is the second equation that I have. So b phi, let's write what b phi is equal in the lab frame, in the rest frame, sorry. This is equal to b phi divided by gamma. And I have two regimes here. So when r is smaller than rl, where I'm inside the light cylinder, there is a, like, very close to the axis over here. Okay? When r is smaller than rl, gamma is equal to 1. And when gamma is equal to 1, b phi is just equal to, b phi in the rest frame is just equal to b phi in the lab frame. And b phi in the lab frame is equal to r divided by rl times bp. So in this regime, this is equal to r divided by rl times bp. And when r is larger than rl, okay, gamma is proportional to r, okay, gamma is actually equal to r divided by rl, so b phi divided by gamma is just bp. Okay? So what does b phi do as? When r is equal to 0 and I'm on the axis, there is no toroidal field in the rest frame. So b phi increasing linearly until it reaches RL, and when it reaches RL, it is equal to BP, and from there on, it is continued to be equal to BP. But this is not surprising because this is the definition of the first acceleration regime. The definition of the first acceleration regime is that I have equilibrium between b phi and BP. So I just rewrote it here in a different way. Okay? But if we have that, and we want to see the structure, we can just take this and put it into the differential equation and derive a structure of b phi and bp as a function of r. So we place that in the differential equation, and what we get is that if you put bp into f, what you will get, I will just write it down because we're starting to be shorter with time, but you can do it and it's in the note. So what we'll have is that placing b phi into the force equation and solving it, okay, under two approximation. In the approximation that r is much smaller than rl, we use the approximation that bp is much larger than b phi, okay? Because when r is much smaller than rl, this quantity is much smaller than 1. So I have only bp, okay? B phi is, I'm approximating it to be 0. And when b phi is 0, all I have is dbp. This is b phi square plus bp square. So I have left with is dbp to dr equal to 0, which means that bp is constant. Okay? And in the limit where r is much larger than rl, I have bp is equal to b phi. And when I use these two limits, what I get is that b phi is equal to some b phi L, b phi on the light cylinder, and we got that already, r divided by RL, and this is r divided by RL to the power of minus 1/2, and BP is equal to BP on the light cylinder. These two quantities are actually roughly equal, and this is equal to, and this times, this is some constant, some c, and this is, actually it's 1. This is r divided by RL to the power of 1/2. Okay? This limit is r smaller than RL, r larger than RL, r smaller than RL, r larger than RL. So this is the profile. And again, I got the profile by getting this and placing it into that and solving. So the profile looks something like that. B phi linearly increasing until RL, and then it decreases like r to the power of minus 1/2. This is B phi. And BP is constant and going down like that. Okay? So this is the profile in the first acceleration regime. Okay? Where I have small r.
Is it not a small r?
No, it's big R. I don't have small r's here. Everything is cylindrical. So everywhere you see small r, it's big R.
But so if it's large r much less than RL,
yeah.
And then you get two cases for this in the case that it's...
No, this is BP, and this is B phi. You have two components of magnetic field. Each one behaves differently in this regime and in that regime.
All right,
Okay?
So just to see if I understood, inside the light cylinder you have BP that's bigger than...
You are dominantly poloidal. Your magnetic field is dominantly in the z direction. And outside, there is equilibrium. Both components are similar and they drop very slowly.
Like 1 to the...
Power of minus. What? Minus 1/2. This is minus. Yeah. Sorry. This is minus. Okay? Now, by the way, just to if I want to see what is the current distribution that supports this, I need a current distribution that goes all along the z, all along the jet. Okay? If I have magnetic field that changes linearly with r here, this is a current distribution that is uniform, and here I have some current distribution that continue onward, current along the jet, and that current, remember, if I want to produce a B phi, I need a current, right? Electricity, first year of electricity. If I want toroidal field, it's supported by a current. So if toroidal field goes slowly with like r to the power of minus 1/2, I need current distribution all along the jet. Okay? Now in the second regime, let's look at the second regime. Okay? Let's skip that because I need it. And now let's look at the second regime. So in the second regime, okay, I have B phi much larger than BP. Okay, the second regime is happening when I'm dominated by toroidal field. Okay, so here I have B phi much larger than BP, and this is happening at R much larger than RL. Okay, because at R smaller than RL, by definition, I'm subrelativistic, gamma is about 1, and I cannot lose causal contact. Okay, so in this case, if I will use this approximation, and again, I have that in my notes, and solve that, what I will get is that BP, again, it's radii that are smaller, that are much smaller than RL, I still in the limit where BP is larger than B phi. Because B phi still will increase radially. But outside of the light cylinder, B phi is now dropping slower than BP. And if I will solve that, and again, it will be in the note, what I have is that BP is proportional to, again, 1 when R is much smaller than RL, R to the power of minus 2 when R is much larger than RL, and B phi will be proportional to R divided by RL when R is much smaller than RL. Okay? And this will go like R to the minus 1 when R is much larger than RL. Okay? So in the second case, the behavior will be different. Let me just erase this so I can plot the two cases here and here. So in the second case, this is case 1. And in case 2, what I have is that, again, this is the light cylinder. BP drops like that, and B phi drops like that. So this is B phi, BP, and BP. Okay? Now B phi that drops like 1 to the power, like R to the power of minus 1, which current distribution support that? If I have a wire with a current, what is the profile of the toroidal field around it? How does the toroidal field goes? Exactly, R to the minus 1. So I have a linearly increasing toroidal field that decreases to R to the power of minus 1. Where is all my current concentrated? Inside the light cylinder. So in the second acceleration regime, all my current is here. And I have no current outside the light cylinder. So I have a very narrow current column. Okay? So without knowing anything about jet stability, which configuration do you think will be less stable? One configuration where I have evenly distributed current, I have motion of charges all along the jet, and another configuration where all my currents are concentrated in a very narrow regime inside the jet. So which one will be harder to maintain? The second, exactly. The second configuration will be less stable than the first one. Okay? And this is what happens. Jets that are accelerated in the first acceleration regime, these types of jets, will be more stable than these types of jets. These jets will start to behave erratic, to show erratic behavior. It's called kink instability, and they will start to wrap up around themselves and become unstable. Okay? Everyone with me? Good. So if I am able to maintain efficient acceleration, my jet will be stable. If I'm not efficiently accelerated and I'm going into a situation where the toroidal field dominates over the poloidal field, my jets become unstable. Okay? And since I don't have much time, I want to show you some slide that will wrap things up. Okay? The exact condition for stability I will show in the note. I don't think it's terribly important for now to understand the idea about jet stability. So jet stability is into the profile of the magnetic field. If the profile of the magnetic field is such that there is equilibrium between toroidal and poloidal field, the jets will be stable. If we are dominated by toroidal field, the jets are unstable. Okay, so everything we discussed about so far is about jets that are steady state, that are not evolving. Okay, I have some funnel, I have some external medium, and this is the shape of the jet. Nothing changes here. And over here, okay, when I'm looking at the configuration of the field, and this is the configuration of the magnetic field from numerical simulation to the numerical simulation of cylindrical jet, the jet accelerated and then continued in a cylindrical cavity. And here you see the profiles of the magnetic field. This is B phi, this is BP, this is r to the minus 1/2. You see B phi increasing up to the light, up to something like the light cylinder, and then it starts to decrease, like r to the power of minus 1/2. Okay? And this is the Lorentz factor. It's increasing linearly all the way to the edge of the jet. First acceleration regime, just like what we derived from the force balance equation. Okay? Now, real jets are, when they propagate in medium, the situation there is somewhat different. And I want to briefly show you what happens when the jet is propagating in a medium. Okay? So here is the jet. The jet is propagating inside the medium of a star. Remember I told you that in gamma ray burst we have a jet breaking out of the star. So when the jet propagates in the medium, it needs to push the material ahead of it. And it acts like a piston. So this forms a bow shock, okay, around the jet. This is the bow shock, okay? And this part of the jet, which is also shocked, becomes to move slower than the rest of the jet material. So I have a bow shock, I have a reverse shock, and this is the head. I call it the head. This part moves slower than the rest of the jet, okay? The medium, the material that is crossing the bow shock from here and that is entering the head from below is spilling sideways, producing a hot bubble, which is called as cocoon. This is hot gas. This is pressurized gas, okay? And this gas basically compressed the jet to roughly a shape of a cylinder because the pressure profile in the cocoon is roughly uniform. And remember when we studied that the jet radius acts like the pressure profile to the power of 1/4. And if the profile is 0, the radius doesn't change. The jet is roughly cylindrical, okay? So I get the collimation until I have pressure equilibrium, and from there on the jet will roughly be cylinder. Okay? The jet shape is close to a cylinder, as I said. Okay? Now inside the jet, these are the magnetic field that we discussed, and this is how they return. Okay? So the thing is that the existence of this head kind of a little bit changes the relations that we derived. Why? Because now here I have a spring, and the spring wants to expand freely to the configuration in the first regime that we discussed about here. The problem is that I have the head, and the head prevents it from expand as fast as it wants. It's like a weight that I'm putting on a spring. And what will the weight do? It will compress it. And what does a compressed spring, what happens to the toroidal field? It's increasing. And if the toroidal field is increasing, I can no longer be in the first regime. I need to be in the second regime where B phi is much larger than BP. Okay? So in this regime, I have a different configuration where B phi drops lower than B phi. And this configuration, what did we say about it? Is it stable or unstable? It's an unstable configuration. So if I have a head, the head will produce instabilities in the jet. So this is a jet without a head with an open funnel. This is a jet that is pushing a medium. Here you have the jet inside. This is this is the Lorentz factor. This is outgoing field lines, and these are returning field line. Inside this part is the jet, and outside here is the cocoon. This is the profile of the magnetic field. You see that B phi here drops like r to the power of -1. The Lorentz factor is increasing up to the point where B phi is equal to BP, and at this point it's about 1. This is gamma beta, okay? It's not the Lorentz factor. And from there on, it's roughly constant. I have a very inefficient acceleration, okay? And BP drops very fast. So this is a headed jet. And headed jets are less stable than non-headed jets. So when the jet propagates inside the medium, the existence of the head will make it non-stable. And this instability will bring dissipation into the magnetic field. Okay? So these are stable jets and these are non-stable jets, and the difference between them is the configuration of the magnetic field. Okay. How much time do I have, Sasha?
5.
5? Can we make it 10?
The expense of the next coffee break, so you don't get coffee.
I didn't get coffee in the morning also. Okay. I just want to briefly, this we discussed, I don't want to talk about it. I just want to briefly go very fast on the different regions in a jet as they propagate. Okay. This I don't want to talk about. Come on. Okay. So let's, So what is happening when I'm launching a jet into a medium? So how does the jet form in the first place? Okay, so assume that we have some compact object and it's threaded by magnetic fields, and I want to produce the jets. I'm starting to spin it. I'm producing toroidal field. Toroidal field expands outward. However, unlike in the ideal case, it expands outward and it meets a medium. And when it meets a medium, it cannot expand anymore. So the central object continues to spin, continue to wind the magnetic field, but nothing can move outward because I have a dense medium around me. This is what happened at the center of a star. Okay? So when I continue to wind the magnetic field, I'm increasing the toroidal component of the magnetic field. Remember what I had from the force equation. What is this? This is tension. This is called hoop stress. This is the stress that wants the magnetic field to contract. And when the toroidal field becomes large enough, this term becomes very large. So what does it do? It makes the rudder band contract. So this contraction takes the poloidal field, takes the magnetic field lines, and push them closer to the axis. So as I'm getting pushed closer to the axis, my energy density flux increasing. I'm pushing at a harder force on the medium, and at some point I'm narrow enough so the jet starts to propagate. Okay? And as the jet starts to propagate, it forms its cocoon, like we discussed before. So in order to produce collimated jets, I must have a medium. Okay? Now, this is a situation that happens when the jet is already evolved. So this is the central part of the jet. Over here, magnetic field lines. These are magnetic field lines. Magnetic field lines expand. Sorry, these are velocity curves. So the motion is along the poloidal direction. Over here, the motion is roughly radial because my pressure is very high. As I move outward, my pressure decreasing. And at some point, the pressure in the jet becomes equal to the pressure. Remember, over here, I have a cocoon. So the pressure becomes equal to the pressure in the cocoon, and my cocoon starts to affecting me, and it starts to get collimated. Now, when I'm accelerating here, I'm accelerating linearly. Remember when we discussed the different acceleration regime, what happens? When I'm accelerating in a radial configuration, I'm accelerating up to a point where I'm losing causal contact. And at this point on, I'm accelerating inefficiently, and my toroidal field becomes very large. Now, toroidal fields have hoop stress, but in order for hoop stress to act, I need to have strong causal contact. Otherwise, I don't know I have a tension. But I'm accelerated out of strong causal contact. So the fact that I'm having a hoop stress doesn't matter. The jet continues to expand radially until it meets some external medium that starts to collimate it. As it starts to collimate it, what does it do to the opening angle? Decreasing the angle. So at some point I will regain causal contacts, because remember, the condition for causal contact is gamma theta smaller than 1. So I will get into a situation where theta is small enough and I will get strong causal contact back. But now what's happened to the ratio between poloidal and toroidal field? Which field is the dominant field now? Remember, I accelerated out of strong causal contact initially. Over here, I'm accelerating out of strong causal contact. So I'm dominated by toroidal field, and I have strong causal contact. I have cylindrical jet dominated by toroidal field, but the toroidal field is so large that this quantity overcomes this quantity. So what I'm getting? Contraction. I have tension. My magnetic field has tension, and now it suddenly realized that it has tension. It accelerated out of causal contact. Toroidal field dominated, but it didn't matter because I wasn't aware that I'm part of a loop. And then all of a sudden I get contracted and I realize, oh, there is a loop. I'm part of a spring and there is tension here. And the tension, what it does, it's getting a shrink. So someone asked how I can create a nozzle. This is a nozzle. The nozzle is produced by the regainment of strong causal contact in a field that is dominated by toroidal field. And this nozzle, as the flow contracts inwards, I still have a flow which is dominated by toroidal field. Toroidal jets are non-stable, and I start to develop instabilities here, and I got a lot of dissipation from the instabilities. We did not discuss that, but instabilities causes magnetic field to start to behave very erratically, start to reconnect, and we get dissipation. Okay? So this is what I said in what I wrote in Word. Okay. So in this nozzle, I got a lot of dissipation. Now, this dissipation is doing something. When I dissipate magnetic field, I'm taking magnetic energy and I transform it into thermal pressure. Okay. So the jet above the nozzle. Okay. This I want to skip. So this is. It's hardly seen. Can I see it over here? Okay. So the jet above the nozzle, here what I'm showing, it's very, very hard to see, but this presentation is going to be on the site. What we see here is the sigma parameter. Remember, is the ratio between magnetic field and mass density. Actually, this is the beta. This is the ratio of the magnetic field and the thermal and the thermal energy. So over here, red color means that I'm highly magnetized. And this is the nozzle, and above the nozzle it's hardly seen, but you see that it's definitely not red. So not red means that that the magnetic fields are decreasing. I had dissipation here, and this dissipation is coming from the instabilities. So the jet above the nozzle, the magnetic field is much lower, and these jets are more stable. So this nozzle gives me dissipation, as this dissipation brings me back some stability into the jets. Okay? So above the nozzle, and I will not discuss it. Above the nozzle, this is the origin of the jet. It's very hard to see, but the jet above it can be much, much more stable. So the dissipation is inherent if I want my jets to become stable enough to be able to break out of the star. Okay? So let me wrap up here, because there is much more that I wanted to say, but I don't have time. So I will just conclude what we discussed about here. Okay? So we started by talking about jet acceleration. I explained to you about the different regimes in jet acceleration. I show you that in order to get efficient acceleration, I need two things. First of all, I need strong causal contact, and secondly, I need some equilibrium between toroidal and poloidal field in the rest frame. This is the first acceleration regime. If I'm losing strong causal contact, I'm no longer able to maintain efficient acceleration. My acceleration is becoming, my gamma, my Lorentz factor does not decrease efficiently, and I'm starting to become more and more dominated by toroidal field. Toroidal field domination gives me an inefficient acceleration, okay? And jets that have different configuration inside them, okay? Eventually, the final condition for acceleration is that if I'm not strongly causally contact, I at least need to be sub-fast magnetosonic. When I'm as long as I'm sub-fast magnetosonic, I'm in the second acceleration regime. I can accelerate. If I'm becoming super fast, my acceleration stops. This is the sigma problem that we discussed about. And then we discussed about the configuration of the magnetic field in the first and second acceleration regimes. First acceleration regime, there is equality between toroidal and poloidal field. These jets are stable. second acceleration regime, B phi dominates. These jets are less stable. Okay? And then I showed you that if I'm taking jets that are in the second acceleration regime and I collimate them and regain causal contact, I'm allowing the jets to become unstable. And this instability gives me dissipation, and this dissipation transforms the magnetic pressure into thermal pressure. And this is actually partly the solution for the sigma problem. Because remember, in the sigma problem, we said that we can only accelerate up to sigma equal sigma 0 to the power of 1/3. This is very large sigma. This dissipation will bring me all the way down to sigma equal 1. Very fast. Beyond that, I still need another process to work, and that's a topic for a different story. So I will end here. Thank you. Yes?
So does all this depend on the central engines, like the colloidal and toroidal field from the beginning?
One of the problems with simulating magnetic field is that the evolution of the jet and the properties of the jets at large distance depend on what you assume on the configuration of the magnetic field at the center. So that's why when we run our simulation, we try to inject the jets as physically as possible by spinning up some compact object that is rotating, but not just injecting and inventing some jet configuration. Because this will give us different, inventing jet configuration will give us different acceleration profile and different stability properties. Yes?
I have two questions, but one is very short. When you showed the picture of the nozzle, at what distances are we talking here from the central engine?
Okay, so this is a good question. It depends on the profile of your medium. If the density profile of the medium decreases very, very sharply, if you have a medium that becomes tenuous very fast, okay, so the jet will be able to open to very large distances before it gets collimated, and then the nozzle will be far from the origin. If you have medium that are very, very dense, then the collimation would happen at very small distances, and the nozzle will be close to the origin. It depends on how high your collimating pressure is relative to the jet luminosity. The higher the pressure, the closer the nozzle will be to the origin.
And what's close and far away here?
Well, it can come to, I don't know, if you have a black hole, it can range from several tens of Schwarzschild radius to 100,000 and even 10 to the 5. And, you know, the situation is also evolving, because what I didn't tell you is that when the jet continues to propagate, right, you have this cocoon, and the cocoon is expanding. Now, the cocoon is like a bag of energy. So when you start to expand it, you increase the volume, the pressure, which is the energy per unit volume, decreasing. So with time, what happens is that the pressure in the cocoon decreasing, the jet becomes collimated at higher and higher altitude, and this nozzle moves upward. So it starts with very close, I don't know, tens of Schwarzschild radii. It can move far, far away depending on how large the medium is. Yes?
I have two questions, but again, one is very short. And the first one is when you said that the dissipation transfer part of the energy into thermal energy.
Yes.
It may have to accelerate the wind, but this time is...
You can use this pressure to accelerate the jet afterwards.
But this isotropic energy is not just directed upwards, so it's...
No, well, you already have a blob that is moving at some small Lorentz factor, but it moves. So if these things will break out of the star, now you have something that from below it is pushed by the jet, and above it you have nothing. So things open up. So the pressure, you have a pressure gradient, and you start to accelerate. So this pressure will give you acceleration outside of the star.
And second one is for what concern the potential of jets in AGN when they hit the intracluster medium.
Yes.
So I imagine that for what you said before, that there is a almost critical separation between the headless regime jets and the one instead that have a kind of head or...
So you're asking what happens to the jets once they break out of the medium. Can I treat them as headless jets?
And in case which are the consequences for the ambient medium?
Okay, so short answer is yes. Eventually you can do that. The longer answer is more complicated because then it depends on the lifetime of the engine. At some point your engine stops working, so then it depends how much it takes the jet to break out. And the effect on the medium, remember that the effect on the medium, the jet itself is very, very narrow. So the effect on the medium is basically the distribution of the energy into the medium through the cocoon. The cocoon is much more, occupied a much larger volume. But the energy density is the cocoon is dominated by everything that you did up to the point that you become headless. So this gives you sort of a filter, if you want. Like it's like an average thing. The effect on the medium is the effect of the jet average over the entire duration that it moves. Okay, so it's kind of like a combination between the two parts. The stability in the jet, I think, eventually should change. The stability properties of the jet. Headless jets are more stable, so it is likely that what's happening that when the jet is breaking out from the core of the galaxy and expands freely, after you have sort of like a refraction wave that is going into the jet, reaching the engine, and from there on, jets will tend to become more stable even than before the breakout. But more stable, yes. Because you don't have the head anymore to compress the magnetic field. So you have like a free evolution and poloidal field will be larger. More questions? Okay, you are looking in a state of a shock or incredibly tired. I don't know which of the two, but
In a state of
anyway.
warm coffee.
Yes. Okay.
Thanks.
So let's have some coffee.